So today we're going to be talking about rational expressions. And we're going to have to learn a few things about domains. And we're going to have to do some simplifying of rational expressions. And we're going to do some combinations and do some multiplication and division of rational expressions. We're also going to do some simplifying of complex fractions again. And we're going to rewrite the difference quotient. This is a biggie, biggie. So, the first thing that we really want to talk about are, what are domains? So, really what we just need to think about are all the possible inputs. And usually we denote that as our x values, or variable in this case. So, well, what do you mean by all possible inputs? Well, let's start out with like the worst case scenario, the rational exponents. So let's start out with the first case here. And we'll start with the worst one, the rational exponents. Expressions. Jeez. Okay. So, take for example, say, I don't know, 2x minus 1 over x plus 5. Now, this is a rational expression. It's a polynomial over a polynomial. And what we can actually say here is, if we look at this very basically, we can say that there is some number divided by something, or some other number. We'll call it sub 2. And what's the one thing we know about numbers that we can't do something with them? Oh, that's right. We can't divide by 0, right? This is what we previously called undefined. Well, this is actually what it means is that there is something happening at one of the particular x values, or the inputs, or it limits the domain in a certain way. So in this case, we only have to know when the denominator is equal to 0, then there is a problem. So what we could easily do to find out what values will not work is just by letting the denominator equal 0. So the idea here is we let the denominator, whatever it is, not equal to 0. And what this says is that items not in domain. So these are all the values that we cannot use. So in this case, we could just say that x plus 5 cannot be equal to 0 and solve, and we can clearly see that x cannot be equal to negative 5. So therefore, we have one value where the domain doesn't make any sense. And we can show a picture of that, what the graph actually looks like, and let you see what is actually happening at this particular value. All right, well, let's take a look at the secondary case here. And let's actually just look at polynomials themselves, the easiest case. Well, the polynomials, well, their domains are really easy. And the domain is all the real numbers. And we use this we use a notation to talk about this, and we can use several different types of notations. But one of the nicest things that we could do is we could just say that all the inputs are elements of the reals. So all this fancy little r is saying is all real numbers. Okay. You could simplify this and just say the set of reals as well. But these are all the numbers that you can possibly think of that are real. So let's talk about the middle case. Well, one of the middle cases here, and those are the radicals. And the radicals aren't too bad either. Their domain is quite simple. And the idea here is behind it. So the concept idea, how should we put it? Yeah, I guess it's the best way. Can you ever get a negative square root? And, well, the answer is no. So, well, what does that mean? That means that we have to do some kind of fancy work to figure out the domain here. So if I look at an example, just a short one, and I say that we're looking for the square root of x plus 3. Now, what does this mean, and what does it mean to say that we can use any values of x? Well, clearly in this case, 0 will work. A lot of numbers will work. But one of the numbers that definitely will not work is if we let x to be equal negative 10. And, whoops. And the thing about this is that if we evaluate, then what we can see is that this is the square root of negative 10 plus 3, which is the square root of negative 7. And this is not real. So we have to do some funny things with it. Okay, later on we'll do some more stuff with this, but this is a complex or an imaginary number. Okay, so this clearly does not work. Okay, if I just simplify this and I just say, you know, can you find the square root of negative 49? No, because there aren't two numbers that are the same multiplied together that would give you a negative number. There's just no way to do that. You cannot get, let's make a big X, you cannot get this to work out in the reals. It will not be in the domain. So how do we do this? Well, the easy thing about this is we just have to realize that whatever is underneath the radical here, which is called the radicand, so this is called the radicand, and all we have to do is set this greater than or equal to 0. Because when it's 0, we know that number exists. We know that there is nothing that can be disputed about it. You can find the square root of 0. The square root of 0 is simply 0. But any negative number will not work in this entire scenario. So we let this expression equal or be greater than 0. And when we go about this, we can clearly see that we have to let, in this case, it's very easy to see that we have to let x to be greater than or equal to negative 3. So when we're looking at the domains for each and every single one of these categories, it just takes a little bit of practice to identify which ones we need to set greater than or equal to 0, which are case, the radicals, or all of the real numbers for the polynomials, and the biggie, the rational numbers, which state that we just simply cannot divide by 0. All right, so let's start to do some examples here and start to identify the domain as part of the process. All right, so here we have a polynomial that is 3x squared minus 4x plus 7. And because this is a polynomial, then we can say that this is the set of all real numbers. And that would be just the domain. That would be the shorthand. Or you could simply say that x, if you really wanted to get the technical version of it, then you could say x such that x is an element of the reals. But shorthand is fine. So if we take another example here of finding domain. So if we're going to find the domain, let's try something a little more interesting. So let's try x squared minus 1 all divided by x squared minus 2x, and let's make it plus 1 here. Okay. So what we really need to do is factor the numerator, and we should factor the denominator, okay? And the reason we do this is because there might be similar products. There might be similar factors, I should say. So what we are looking for are like factors. Okay? So what we do know is that x squared minus 1, this beastie right here, is the difference of two squares. So that tells us that we have an x plus 1 times the quantity x minus 1. And in the, let's do a highlighter with light green. And the light green, the denominator here, what we notice is that this is a perfect square. And it's an easy to see perfect square, mainly because if I do this in, let's say, blue real quick, this is a perfect square, this is a perfect square, and if I take 2 times the value of the first beast times the value of the second beast, which in this case would be 1, then we have to end up with the b, which is negative 2. Well, one of these, x or 2, has to be negative, so it looks like we'll probably make 1 to be negative. And we can try that out and see what happens. But trust assured that this is actually the perfect square. So if we place this down now, then this would be x minus 1 all quantity squared. And if you can see that this factor and this factor are exactly the same, except that there are 2 in the denominator and 1 in the numerator, that means that we can simply cancel out, whoops, let me, I wanted to use this pen. And let's just cross out the like factors. So there's one of them is going to be gone, and that seems to be all of them in the numerator, and just one of them is going to be gone in the denominator because there's 2. So this all looks like it crunches down to x plus 1 all divided by x minus 1. So what's the domain for this? Well, the domain, remember, is when the denominator, I shouldn't have said it this way, but the idea here is when the denominator is not equal to 0, then the domain does not make sense. So the domain is when the denominator makes sense. So clearly, the only time when this doesn't make sense is when we let x minus 1 be equal to 0, in which case we can clearly see, not equal to 0, which we clearly can see that x cannot be equal to 1. So what we can say here is that this domain is the set of all real numbers excluding 1. Let's just say it's the set of all real numbers minus the subset of 1. All right. Let's look at some more interesting examples now. And let's start to do some simplifications. So now let's take a look at another example. All right, so now let's take a look at another example in which we have to factor two polynomials. In fact, they're two trinomials, and these are nice ones because the lead coefficient, or a, is equal to 1. So that means all we have to do are find the factors of 20 that combine to 8 in the numerator, and in the denominator we're going to have to find the factors of 10 that combine to 11. So this is not too bad. Looks like we'll have two factors in the numerator and 2 in the denominator, and it looks like they will all have x's because there's only x squared, or 1x squared. So all we have to do is put these together. So it looks like the factors of 20 that combine to 8 would probably be 2 and 10, because if we take positive 10 things and negative 2 things, then we'll get 8 things back. So it looks like we'll have a plus 10 and a minus 2. And in the denominator, well, that one looks pretty easy. That looks like it's 10 and 1. So that'd be plus 10 and plus 1. And what you'll notice here is that we have a factor of 1, so something is going to happen. So we know something is going to happen at x equal negative 10. And what do we know that's going to happen? It's undefined. But we also know something else about this beast right there. And that tells us that if we let x plus 1 not be equal to 0, then it's clear to see that x cannot be equal to negative 1 either. So what we could clearly say is that we can take all values of x, so we can take all x values, but not x to be equal to 1 or x to be equal to negative 10. And the other way to say it is we could do it the same way as before. We could also use interval notation for this with unions. But yeah, okay, let's let's not do that right this minute in this tutorial. So this is another way to represent the domain. All these ways to represent the domain. All right. So let's take a little more complicated example at this point. So here we are, and let's pick an interesting example, and then we're going to simplify. Yeah, let's do that. Yeah, let's simplify it again. And let's simplify something that looks like 4y minus 16 divided by, I don't know, 5y? Plus 15. And let's make that all divided by, let's see here. Let's make this 4 minus y, all divided by 2y plus 6. Why not? Okay. So remember what this is really saying. This is saying that we have this fraction divided by this fraction. Which means that if I looked at this as saying, well, what happens if this is not, these are not the numbers, but let's just say that this is 4 divided by 2. And if that's the case, then that's the same thing as taking 1/2 of 4. So all we have to do is change this to make a little bit easier for us and say 4y minus 16 all divided by 5y plus 15. And instead of it being division now, we're going to multiply by the denominator's reciprocal. So that would just be 2y plus 6 all divided by 4 minus y. Alright, so now, well, what other things can we do to this? Well, we could do a few things, and we could factor out the 4 from this little beastie in the top, and we could factor out a 5 in the beastie down here, and we could factor out a 2 from here. Looks like we have some interesting stuff going on now. And then, this looks a little interesting here, this guy. I wonder if we can play a little game. And let's see, if I factor out, a -1 from here, what would that look like? It would look like negative, and then it would be, well, the y would turn positive, and the 4 would become negative. Oh, look at that. We have some interesting things happening here, don't we? Do 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 do. Hey, look at that. Some things are all going away here. And how do you multiply fractions again, guys? Straight across. So we have 4 times 2, because all of this is gone. So that would give us 8 divided by, well, this is really 5 times a -1, so that would just be -8/5. Wow, that complicated guy reduced all the way down to this. Pretty cool, right? And we forgot to also mention the domain, so let's do that now and say that the domain is all the real numbers except for, well, what are the only values that don't make sense? Well, it's the ones that where they don't make where they don't make sense is where there's zero. So where this is going to 0 and where this is going to 0, so it looks like x cannot be equal to -3 and +4. Alright, so now let's take another look at a different type of example in which we're combining fractions. And these are what we're going to call combining rational expressions. So when we do this, we need to have the same gosh darn denominators. And luckily for us, in this case, both denominators are exactly the same. So that just means that all we have to do is keep the same denominator, because we want to talk about the same whole, and remember that's the total. So what do we do to the numerator? Well, we just carry out what the operation says. So I know that we don't have to this time, but in case this was a subtraction, we might have to do some distribution. So I'm going to play it safe and just put those parentheses here. And now we just do the combination. So this would be 2x minus 1 plus 1 minus x. And then that looks like it's all divided by x plus 3. And then when we do the combinations, we can see that these beasties go away, leaving us with just x divided by x plus 3, in which case we know that x cannot be equal to -3. Example, when the denominators are not the same, and we'll have to do some combinations here. So the first thing, like always, is to really factor out any polynomials, if at all possible. So if we factor out just this beastie over here, we can clearly see that in both binomials there's only one x, and it's got to be -2 and +1, it looks like. And what we can see here is that this is x divided by, well, let me just make sure that doesn't look there. So again, it has to have the binomials, and what we're going to be looking for is either an x minus 2 or an x plus 1. And it looks like here the factors of 6 that are going to combine to 5, and they both have to be negative, so it looks like -2 and x -3 or x minus 3. So here we have the interesting component. Well, what is the common denominator? Well, both of these guys, so if I use red here, both of these guys have a factor of x minus 2. So that's nice to know that they both have the same factor. So if we start to think about what is a common denominator, or what is the ability to make one, well, it just means that they have to be part of the same whole. So we have to make one giant piece here. So if we just take all of the factors and multiply them together, then we have a common denominator. But both of these have an x minus 2. So it looks like what we could say is perhaps the common denominator in this case might be the quantity x minus 2 times the quantity x plus 1 times the quantity x minus 3. So notice we're just taking each one of these. So I'm only taking one of those because there's two of them, and there's one of those and one of those. So I'm just multiplying each one of the pieces together. Now, what do we want to do with this now? Well, we want to make sure that we can simplify this and combine them. So the easiest thing to do would be to multiply this entire thing by that common denominator. And when it happens, you'll notice that the denominators will cancel out if you're actually multiplying through the whole thing. If you want to look at it as a factoring, we could do that too, but I'm not sure which one would be easiest to show right this minute. So let's see, what would be the easiest way? All right, well, I'm not sure that those ways would be good right this minute, but let's see if I can. It's going to look kind of bad at first, but it just know that you're only multiplying each rational expression by 1 when you think about it. And you're going to see what I mean in a second, I hope. So, see how this first term right here has the x minus 2 and the x plus 1, but it's missing the x minus 3. So if we multiply top and bottom, numerator and denominator, by x minus 3 to this first term, then we can see in the denominator here that now we have our common denominator. So now if we subtract off another beastie, and we'll have to figure out what we're missing, and then we're going to multiply this all by x over x minus 2 quantity, x minus 3 quantity. And now we just have to figure out what we're missing down in here. So we all have the x minus 2 now. We have the x minus 3, but we're missing that x plus 1. So we'll have to multiply numerator and denominator by the same beast. So at this stage, we can just follow the general rules of fractions and multiply straight across. So this would be the quantity x minus 3 all over, and I'm going to keep them separate for just a second, but hopefully you see that we can just combine them right away. And I'm not canceling them out because we want them here in this case. So now we have this subtraction, and we have x times x plus 1 in the numerator, and we have this whole beast of x plus 1 times x minus 2 times the quantity x minus 3. So now that we have the common denoms, we can actually just put the numerators over the common denominator. So what this would be now is x minus 3 minus x times x plus 1 all divided by the quantities x minus 3, x minus 2, and x plus 1. And all we have to do now is do some simplifying. In which case we realize that we're going to be distributing a negative x to both of these. And what we have here is x minus 3 minus x squared minus x all over the quantities x minus 3, x minus 2, and x plus 1. And now if we see that there's opposites here, we can now just factor out a negative and have x squared plus 3 in the numerator, and we have x minus 3 times the quantities x minus 2 and x plus 1. I'll let you figure out what the domain here is for this. Alright, now let's start moving into some more complicated problems. And they're not really much more complicated, except that in this case, we just have to do a little bit of trickery. And what we have to notice in both of these terms in the numerator is that we have a 1 minus x squared to some power. And what we have to ask ourselves is, which is the smaller power, or the smaller exponent? And in this case, the exponent is negative 1/2. So what that tells us is that we can factor out a 1 minus x squared to the negative 1/2. Now, it's going to look a little weird, so let's try to take it a little slow. So what we're going to do first is just factor this out. Well, you know what? Let's do both of them. Can you also see in both of these terms that we have also a negative x? So we're also going to factor out a negative x. Okay, we'll do both at the same time. So negative x times this whole kind of, whoops, not this yet. So negative x times the 1 minus x squared to the negative 1/2 power, and now we're going to multiply by what we've taken out. So if we have taken out 1 negative x from here, we're left with x squared. And if we take out 1 of the 1 minus x squared to the negative halves from both of these, well, in the first one, we're going to be left with just 1. So we don't need to worry too much more about that. Now the sign is going to change because we factored out this negative and the negative x. So what's left here is 2 times the quantity 1 minus x squared to the 1/2 power minus a negative 1/2. And the reason being is because, first of all, we're factoring out, which means that we're technically dividing, right? And when we divide like bases, we simply do a subtraction on their exponents. And this happens to be a loss of a loss of a half. So when we pull this all together now, what we have is negative, oh, whoops, almost forgot the little x to the 4th. Okay, So what we have now here is negative x times the quantity 1 minus x squared, all to the negative 1/2, times the quantity x squared plus 2 times 1 minus x squared to the first power, all divided by x to the fourth. And then, if we carry this out even more, and maybe you saw one of the cancellations already, and if you haven't, that's okay. So what we're going to do now is just do the distribution and combine. So we have x squared plus 2 minus 2x squared. So we just distributed. And now we'll just finish off the simplification. And this is what we were talking about. Perhaps you saw this already, but what we have here is an x in both top and bottom, and what's left down here are 3 of them if we get rid of 1 in the numerator. That means we get rid of 1 in the denominator, and that was that subtraction. And then we can rewrite this as negative, well, it looks like it's negative 2 minus x squared, all divided by 1 minus x squared to the 1/2 power times x cubed. And then if we just take it one more step and try to get rid of this negative, and if we factor out a negative here, then we'll turn this negative into a positive. So the final report looks like it's going to be x squared minus 2. So we just changed the signs. And we factored out the negatives so that this would be 2 negatives, a negative times a negative. And it looks like we are good to go. Now technically we could rationalize, but let's leave this alone for right now. And I'll let you come up with the domain. Alright. Now I really just want to get to the biggie. And this is the biggie. So, yeah, I don't know if I want to do it. I really do. Okay, the difference quotient. This is power. And it does a lot. So I'm not going to tell you the whole story, but I'm going to give you a good portion of it. So what I'm just going to define first is delta x. So I'm going to call this delta x. And what does delta start with? It starts with a d. So this is a difference between x's, okay? So there's some difference between x's. And what the difference quotient is, I'm not going to tell you what it actually equals, okay? That's technically for another course. But what we can say is that some function evaluated at some input plus the difference in those in the x's or those inputs, and we lop off the height at that particular input and we divide it by the interval of the input, then we can come up with something really powerful. So we're going to use this massively powerful idea, and we're going to play around with it just a bit. So what happens if we took something that looked like 1 divided by x plus delta x all squared, and let's say that this is 1 over x squared, and it's all over delta x. So there's a lot of ways to tackle this type of problem, and I'm not sure which way you want to do it first. I mean, one of the best ways is to actually factor out that delta x in the massive denominator, but I'm not sure if that's going to be easily seen or not. So let's actually make common denominators first. Well, all right. So let's do that. Let's factor out the delta x. So 1 over delta x times this whole monstrosity. And now what we need to do is combine these two rationals. And it's kind of easy to see that the common denominator in this case is simply going to be x squared times the quantity x plus delta x all squared. And that comes because this times this is the only way that you're going to figure out about the common. Well, by doing that, that just means that we have to multiply this now. So we have 1 over delta x times, well, what we have here is we're going to have to multiply this by x squared over x squared times that first beast. And then we're going to have to subtract, well, it looks like x plus delta x squared over x plus delta x squared. And we'll have to multiply that by what was left. So now if we just multiply straight across and then combine, we end up with 1 over delta x all times something in the numerator, but the denominator we made sure was the same. So what we have in the numerator now is x squared minus the quantity x plus delta x squared. And because that's a perfect square, it's easy to deal with. So we can now do x squared minus x squared minus 2x delta x minus delta x squared. And if you don't believe that that's the expansion, I encourage you to prove me wrong and try it out for yourself. And we have in the denominator nothing. We're not going to bother multiplying this, okay? And then you'll notice something interesting happening. The x's cancel out, and we can factor out a delta x, 1 delta x, from each of the remaining terms in the numerator. So that means that we have 1 over delta x times, well, that looks like delta x times negative 2x minus delta x. Oh, that's interesting. Wow. You see it? Look at that. We're dividing and multiplying by delta x. And then we can factor out a negative. And then we can factor out a negative. So our complete solution here is going to be negative, what was it, 2x plus delta x all over x squared plus delta x squared times x squared. By the way, what did we just divide by?